Series and parallel circuits are absolutely critical in understanding the electricity topic. We're going to look at how to draw a parallel circuit, and the three main parts of this video are looking at how current, voltage and resistance behaves in a parallel circuit. A series circuit is arranged so the electrons can flow through each component one after the other. This is an example of a parallel circuit where the wire splits up and allows the current to flow through each component at the same time. In this example, we have a cell at the top, we have a thermistor, a resistor and a lamp, all parallel to each other, and this is what defines a parallel circuit. We looked in the other video at how cells act in series. So now we're going to look at how cells act in parallel. If we start with a simple cell, which is with 1.5 volts, then if we add them in parallel, then we still get 1.5 volts. So the voltage is unchanged. There are three things we need to learn about in parallel circuits, and they relate to current, voltage and resistance. This rule relates to current, and it says that the total current that flows into a junction must equal the total current flowing out of a junction. Let's take this example on the left. If we said that 20 amps flowed out of the cell and down this wire, we can see that it's come to a junction, and that one wire splits into two. If we said, just for an example, that 3 amps flowed through the thermistor, then we can see that 17 amps must flow down this wire here. And that's because the 17 and the 3 flow out of the junction must equal the 20 amps that flowed in the junction. We can now see that that 17 amps comes to another junction. If we said, for an example, that 8 amps flowed through that resistor, that means 9 amps must flow down this wire. And because there's no other branches, there's still 9 amps flowing down this lamp, or through this lamp, sorry. Now you know that, have a pause of the video and try and work out what X, Y and Z are. As you can see from this diagram, the 9 amps from that bulb can't go anywhere. So therefore X must be 9 amps. Then that 9 amps meets another junction where it combines with the 8 amps. Therefore they will meet and add together to give Y, which will be 17 amps. Then the 17 amps will carry on up that wire and combine with the 3 amps from the thermistor, and therefore Z will be 20 amps. Another thing you should be able to notice is that 20 amps came out of the cell, and therefore 20 amps flows back into the cell. The next rule looks at voltage in parallel circuits, and this rule says that the voltage is the same for all components in a parallel circuit. Have a look at this diagram on the left. The cell at the top is a 50 volt cell. Therefore, the thermistor must have 50 volts. The resistor must also have 50 volts, and the lamp also has 50 volts. Now this is quite easy to imagine if you think about each component is touching each side of that cell. Therefore, it gets all of the energy from the cell before it can travel through the component. The last thing we're going to look at is resistance in parallel circuits. In a parallel circuit, the total resistance is less than the individual resistances. Now this is quite tricky to understand, so I've put some numbers in for you. If we look at these three resistors, they have a resistance of 2 ohms, 3 ohms and 4 ohms. But the total resistance for this circuit is 1 and a bit ohms, which is less than all three. Now that's really hard to imagine, but if you go back and watch the video called the Great Resistance Analogy, you'll be able to try and work out how this is possible. The reason why the total resistance is less than even the resistance for each individual resistor is because the electrons can travel through more than one path. So therefore the total resistance is less. Have a go at these questions. Pause the video, have a go, and on the next slide you'll be able to see the answers. Here are the answers. The answer to question number 1 is 100 volts, and that's because the resistor is touching each side of that cell. Therefore the cell can give the electrons all of the energy before they travel through the resistor. Question number 2 is also 100 volts because again that lamp is touching both sides of the cell. And that's the same for every component in parallel. They will all have 100 volts. Question number 3. We can see from the ammeter that 0.5 amps is travelling down that wire. Then it comes to a junction and the question says that 0.3 amps flows through that resistor. And that must mean that 0.2 amps is left to travel through that light bulb. Question number 4. How much current flows back to the cell at the top? Again, it's 0.5 because the 0.2 from the lamp combine with 0.3 from the resistor to form 0.5 again before it goes back to the cell. Question number 5, calculate the resistance of the resistor, and for this we use Ohm's law, which is V equals I times R. If you plug in the numbers you'll be able to get that answer. And question 6 is exactly the same. We use V equals I times R. We know the voltage from the question above, and we know the current from the question above. And once we solve the equation, we'll see that the bulb has a resistance of 500 ohms. Some more questions. Have a go at this, pause the video, and I will give you the answers on the next slide. Here are the answers for this slide. Question number 1, the highest resistance is the 14 ohm resistor. That's quite an easy one because they're all labelled with their resistances. Question number 2, they all have the same potential difference, and that's because all of these components are in parallel. And in a parallel circuit, all of the components have the same potential difference. Question number 3, if they have the same voltage, what's the difference between them? If they're a different resistor and they all have the same voltage, what's the difference? The answer is that they have a different amount of current flowing through them. And the 14 ohm resistor will have the least current, and the 12 ohm resistor will have the most current. If you're unsure about why this is, look at the video called the Great Resistance Analogy, and it will try and explain that resistance tries to oppose the motion of the current, and therefore less current will flow through a higher resistance. The next part is quite tricky. If you're not feeling very confident at this point, then watch the video again and have a go at the questions. If you feel like you understand up till this point, have a look at the next slide. We're now going to find the exact value for the total resistance. If we have a look on this diagram on the left, we have 3 resistors. We're going to call them R1, R2 and R3. And we want to find a value for the total resistance, which we're going to call RT. To find that, we need to use this equation. And this is why it gets quite tricky. To make it simpler, I'll try and use some numbers and I'll show you some workings to show you how to use it. This example now has 3 values for resistance on those resistors. We know we need to use this equation at the top here, so the next step is replacing those letters with the numbers from the question. We know that 1 divided by the total resistance is equal to the sum of these fractions. If we use a calculator, we can find 1 over the total resistance is equal to 19 over 20. But this is equal to 1 over the total resistance. So to find this answer, we can do a little mathematical trick. If you have 2 fractions on each side of the equal sign, you could flip both of them upside down. So therefore, the total resistance is equal to 20 over 19. If you wanted to put a number on that, the total resistance is equal to 1.05 ohms.